Hi everyone, this is Becky, and in this video we are going to take a look at writing and balancing chemical equations. So the goals of this video are for you to be able to balance a chemical equation for mass, to be able to interpret a chemical equation and to write a balanced equation from a written description, and then to be able to go between particle level diagrams and chemical equations and from equations to a particle level diagram. Okay. All right, so we talked about these chemical equations before, and we've said that they are symbolic representation of a chemical reaction, right? So it's a chemical reaction where, say, for example, I have a solid A reacting with gas B at 100 degrees Celsius, turning into AB2, which is a solid. So this gives us, these chemical equations give us a lot of different information, right? Remember, the things that are written on this side of the chemical equation are our reactants. The things that are written on this side of our equation are our products, right? We have the formulas for each. We have states of matter. And then on or around above the arrow, here's where we can write reaction conditions. Like, so for example, if a reaction needs to happen at a particular temperature, so temperature, we can have catalysts would be here. Any other kind of conditions that are necessary for the reaction to proceed would be written above or below the arrow. So the one thing about chemical equations, the symbolic representation of a reaction, is that it must, absolutely must, no matter what, reflect conservation of mass. So we know that in a chemical equation or a chemical reaction, atoms aren't created or destroyed. So chemical equations need to reflect this, which means that they have to have the same number and type of atom on each side of the equation. So in the reactants and in the products, they have to have the same. And to do that, what we're going to do is we're going to use coefficients. So for example, so in this reaction that I have up here, right here, I have 1A is reacting with 1B to produce a molecule or a unit that has 1A and 2B. So I have 2B on the product side, only 1 on the reactant side. So to balance that, to make it account for mass, I need to put a 2 in front over here. So in terms of balancing equations, what we're going to do here is we're going to add coefficients or numbers in front of the symbol to change the number of units of each species. Each species is just whatever it is that I'm reacting. So here in this equation that we have over here, remember, like, so if I think about species A and species B, the element A and element B. So on the reactant side of the equation, I have 1 atom of A. On the product side, I have 1 atom of B. On the reactant side, I have 1 atom of B. On the product side, I have 2 atoms of B, right? So in order to get 2 atoms of B on the reactant side of the equation, I'm going to put a coefficient. So I'm going to put a number in front of that unit of B. And that unit of B, I'm going to put a 2 there, which changes this to 2 units of B. So I have 1 on A on each side. I have 2 B's on each side, which means that this equation is balanced for mass. So a couple of things to keep in mind about this idea of a coefficient. The coefficient applies to everything that follows in the unit. So for example, if I have zinc chloride and I put a coefficient in front of it, so I put a 2 in front of it, that 2 applies to the zinc, but it also applies to the chlorine. So this gives me 2 zinc and 4 chlorine on that side or within that species of the reaction. And then remember, and this is, we've talked about this before, but just we're never, ever, 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 ever going to change the subscripts, because remember, it's the subscripts that tell us what the stuff is. If I change the subscript, I'm changing the substance itself. I never want to do that. What I'm doing is just making it reflect conservation of mass. So I'm just making it reflect the same number and types of each atom. So I'm not changing the reaction that's happening. And if I change subscripts, I'm changing the reaction that's happening. An example of this, looking at this equation where I'm burning methane and oxygen. So I'm burning methane in air, I'm getting CO2 and H2O. So if I'm going to look at this, I'm going to set up my chart here where I'm going to identify each type of thing that's in my reaction. I have carbons, hydrogens, and oxygens. On the reactant side, I have 1 carbon, 4 hydrogens, and 2 oxygens. On the product side, I have 1 carbon, 2 hydrogens, and 3 oxygens. Okay, so to do this, what I'm going to look at, so I have to balance this equation. I'm going to do the things that I can apply as single atoms. So for example, oxygen, because I can change the number of oxygen without changing anything else. I'm going to do that last. So starting out with carbon, carbons are balanced. They're good. I have 1 on each side. I have 4 hydrogens on the reactant side, 2 on the product side, which means I need a 2 in front of that H2O. That changes the number of hydrogens on the product side from 2 to 4, and it changes the number of oxygens from 3 to 2 here plus 2 here to 4. Okay, so hydrogens are now okay. I look at oxygens. I have 2 oxygens on the reactant side. I have 4 on the product side. So I need to put a 2 in front of that oxygen, that O2, which changes that to 4. Okay, double checking. I have 1 carbon, 1 carbon, 4 hydrogens, 4 hydrogens. 2 plus 2 is 4 oxygens, and then 4 oxygens on the reactant side, which makes my equation balanced. So, pro tip, do single atoms last. All right, if we can do something as a single atom, if it's something we can change one thing without changing everything else, do it last. All right, another example is something like this, where I'm mixing 2 solutions together and I'm getting a precipitate. So this is a precipitation reaction, and this one looks really kind of complicated, but notice a couple of things. I have nitrates on both sides of the equation, and I have carbonates on both sides of the equation. The nitrates and the carbonates aren't changing, so I'm going to balance those polyatomic ions as a group because they're not changing, so I'm not going to worry about the carbons and the oxygens. I'm just going to worry about the carbonates and the nitrates. So the species that I have involved here are going to be aluminum, nitrate, potassium, and carbonate. Okay, so let's start with aluminum, or let's take a look. I have 1 aluminum on the reactant side and 2 on the product side. I have 3 nitrates on the reactant side and 1 on the product. I have 2 potassiums and then 1, and then I have 1 carbonate and I have 3 on the product side. Okay, so in terms of balancing for mass, I'm going to start by putting a 2 over here in front of that aluminum nitrate. That changes the number of aluminums to 2, but it changes the number of nitrates to 6. Okay. Then in terms of, so then the aluminums are okay, but nitrates, I have 6 on the reactant side. I only have 1 on the product side. So I'm going to put a 6 in front of that KNO3. That changes the number of nitrates to 6, but it also changes the number of potassiums to 6 on the product side. I have 2 potassiums on the reactant side, so this needs to be a 3, which changes the number of potassiums to 6, but also changes the number of carbonates to 3, which happens to work out because I have 3 carbonates on the product side and 3 on the reactant side. So then double checking, 2 aluminums, right? 6 nitrates, 2 times 3 is 6 nitrates, 6 nitrates. 6 potassiums, and then 3 carbonates. Okay, so pro tip, balance polyatomics as a unit if they're not changing. Right? If they change, then we have to think about balancing them as a single atom, or as atoms. But if they're not changing, we're going to balance them as a single unit, so as nitrate and carbonate in this case. Okay, and then we get to something that's a little bit more complicated. So I'm burning butane now instead of oxygen. So again, I'm going to have carbon, I'm going to have hydrogen, I'm going to have oxygen. Going through, I have 4 carbons on the reactant side, 1 on the product. I have 10 hydrogens on the reactant side, I have 2 on the product side, and then I have 2 oxygens and 3 oxygens on the reactant and product side. So, all right, again, because oxygen is by itself, I'm going to do oxygen last. I'm going to start with the carbons for funsies. I have 4 on the reactant side, which means I need a 4 in front of that CO2, which changes the number of carbon to 4 and changes the total number of oxygens to now I have 8 plus 1 is 9. Okay, then on the reactant side, I have 10 hydrogens on the reactant side, which means I need 10 on the product side. So I'm going to put a 5 in front of that H2O, which makes that 10, but which also changes the total number of oxygens from 9 to that's 8 plus 5 is now 13. Okay, so the carbons and hydrogens are okay. Oxygens, on the other hand, I have 13 oxygens on the product side. And because this is O2, there is no way for me to get 13 oxygens on the reactant side. Remember, coefficients can't be fractions. They have to be whole numbers. So in order for me to balance this out, I need to take this odd number of oxygen that I have over here and turn it into an even number. The way that I'm going to do that is by taking all of the coefficients that I have and I'm going to multiply them by 2. So instead of this coefficient over here being a 1, it's now a 2. And instead of this coefficient being a 4, it's now an 8, and this is now a 10. Okay, so what this does is it changes the total number of carbons to 8, the total number of hydrogens to 20, and now on the product side, it's changing the total number of oxygens to 26. In order for that to, so now I have 26 oxygens on the product side, I can get 26 oxygens on the reactant side by making that coefficient a 13. So then that gives me 26 oxygens, so I have 8 carbons on each side, 20 hydrogens, and 26 oxygens. So again, if we are encountering, remember we can multiply by 2 if we have an even odd situation. Okay. So in terms of balancing equations, when we're given the formulas for each, it's relatively straightforward. But what if I'm not given the formulas for each? What if, for example, we are looking at writing an equation from a written description? So I have the solution of calcium chloride added to a solution of potassium carbonate producing solid, this description here. So the first step here is I have to write the equation. Before I can write the equation, I have to write proper balanced formulas. Here's that place, remember where we told you that you really need to know how to write formulas for ionic compounds? Here's where this comes in. Right, we need to make sure that we're writing proper formulas. So remember that calcium here has a 2+ charge, chloride is 1-, potassium is +1, carbonate is 2-. All right, so Ca 2+, CO3 2-, and then K+ and Cl-. So when I write my proper formulas, so if I'm mixing together these two solutions, these are going to be reactants. These are products. So I have calcium chloride, so CaCl2, as an aqueous solution, is added to potassium carbonate, K2CO3, as an aqueous solution, forming calcium carbonate as a solid and potassium chloride as an aqueous solution. So now that I have an equation that has formulas for each of the reactants and products, I can do that same thing that we were doing before in balancing it. I'm going to look at calcium, I'm going to look at chloride, potassium, and I'm going to look at carbonate as my 4 species that are involved in this reaction. Okay, 1 and 1, I have 2 and 1, I have 2 and 1, and then I have 1 and 1. So calciums are okay, carbonates are okay, potassium and chloride are not. I need a 2 in front of that KCl, which changes those to 2, which makes this a balanced equation. Okay, so there's just another step here, which involves writing proper formulas. Remember that if you're doing this and you have an equation that can't balance, check your formulas because it's likely that one of them is wrong. All right, another example, doing the same thing. Solid magnesium is added to a solution of silver nitrate, forming solid silver in a solution of magnesium nitrate. So again, here we're looking at proper formulas. That's just magnesium metal. The silver is 1+. Nitrate is NO3-, and magnesium forms a 2+ ion. Nitrate stays as NO3-. And so I'm adding solid magnesium to a solution of silver nitrate, which is just AgNO3 because it's 1-, 1+. And I'm getting magnesium nitrate in solution. And silver metal. All right, that should be AQ. Forgot about my state of matter. And now again, do the whole balancing thing where I'm looking at magnesium, I'm looking at silver, then I'm looking at nitrate. So I have 1 of each on this side, and then I have 1, 1, and 2, which means I need a 2 in front of that nitrate over there, which means I need a 2 in front of that silver over there to make a balance. Okay. So a couple of things as you're doing this and as you're keeping all of these things in mind. This is a lot of trial and error. This is making sure that we're putting together all of these things that we were doing with writing and balancing equations. So for a little bit of practice, what I would like you to do, instead of having a simple question at the end, for this video, what we would like you to do is to do page 20 in your packet. You must try this to get full credit for your homework. So page 20 in your packet. Bring that with you to class next time we meet. We will see you then.